Hi Zach, how's it going? Today I'm going to start with limits. I know it's a topic you've done already in pre-calculus, but I figure since it's useful in calculus, it might be worth it to review. A limit is the value that f of x approaches as x gets closer to a certain value. This could be any number that is on the function, or it could be the end behavior of the function as it goes towards infinity or negative infinity. Limits are useful for evaluating the tendency of a graph as it gets close to a hole in the graph, which is a point where f of x is not defined, or the end behavior if the function has a horizontal asymptote, or if the function goes up to infinity or down to negative infinity. Just a reminder, an asymptote is a line that your function will never cross, but as it gets closer and closer to a certain value, it gets closer and closer to that line. I mentioned at the beginning that limits are useful for calculus. The reason for that is, if you recall from the last video, that integrals are an infinite number of rectangles that have an area that add up to the area underneath the function. Limits can show the area underneath the function as that number of rectangles increases to infinity. You can evaluate a limit by either using direct substitution, that is plugging in the number that you're going towards, or using manipulation to cancel things out. Manipulation can include factoring, multiplying by a conjugate if you have a radical in the denominator or the numerator, or multiplying by a common denominator. Some examples that we have here are, if we have the limit as x approaches 3 of x squared minus 9, we can easily evaluate that by using direct substitution. When we plug in 3 for x, we get 3 squared minus 9. 3 squared is 9, so we'd have 9 minus 9, and the limit as x approaches 3 of x squared minus 9 is 0. If we have the limit as x approaches 1 of x squared minus x over x minus 1, we can factor out an x in the numerator and then cancel out the x minus 1s in the numerator and the denominator. What we have left is the function of x. The limit as x approaches 1 of the function f of x equals x is simply 1. But the function is not actually defined at that value, x equals 1. So we can only say that the limit is 1, not that the function is 1. If we have the limit as x approaches infinity of 2x cubed plus 4x minus 16 over 3x cubed minus 5x squared plus 7, we can see that as x approaches infinity, the terms with a smaller exponent are going to become negligible. So we can focus simply on the terms 2x cubed and 3x cubed. If we reduce our expression down to those terms, 2x cubed and 3x cubed, the x cubed term can cancel out, and we are left with 2/3. So the limit as x approaches infinity of 2x cubed plus 4x minus 16 over 3x cubed minus 5x squared plus 7 is 2/3. If we have the limit as x approaches negative infinity of x cubed plus 3, we simply have negative infinity cubed. That, as you can imagine, would simply be negative infinity. If we had x squared, it would be positive infinity, because a negative times a negative is a positive. But since we have x cubed, it would continue to be negative. Another useful thing about limits is that we can take limits from both the right and left side of the function as x approaches a certain value. So if we have something like the absolute value of x divided by x, which when we graph it, we can see that it doesn't look quite defined at x equals 0. The limit as x approaches 0 from the right side, written like this, would be 1, because a really small positive number divided by a really small positive number, which a really small positive number is something that's close to 0, so we can estimate it to be about what 0 would be. That really small positive number divided by a really small positive number is going to be 1, positive 1. However, if we approach 0 from the left, we have a really small negative number, but the absolute value of that would be a positive number, and that would be divided by the same really small negative number. That value would be -1. So we have two totally different limits when we come from the right or the left of this function. So the limit would not be defined at x equals 0. When this happens, we say the limit does not exist. I have two examples I'd like you to try out for next time. The first is the limit as x approaches 2 of x squared minus 4 over 1 over x minus 1/2, and the limit as x approaches negative infinity of 6x cubed minus 2x over negative 5x cubed plus 4. I will create another video with the solutions to these problems, but I'd like you to try them before watching that video. I'll see you next time. Bye!